Friends, welcome to the lecture 31 on Advanced Steel Design course. We are going to discuss stability functions. I will put as 2. We are continuing from the previous lecture. Okay. In the last lecture, there is a small correction. I apologize for that. Let us rewrite that equation for KPP and KQP. Okay. Please turn back your notes. I am rewriting this equation. There is a small correction. So, KPP is actually given by alpha I times of sin alpha I minus alpha I cos alpha divided by twice of 1 minus cos alpha I minus alpha I sin alpha of EI by LI. So, the error what we had is that this was missing. So, it is written as alpha I sin alpha I minus alpha I cos alpha I, okay, divided by twice of 1 minus cos alpha I minus alpha I sin alpha. This was written, but now the change is, I think there is a whole bracket here, friend. Please make this change. Now this equation is correct. Okay. So, now of course, KQP, there is no change in that. This is alpha I minus sin alpha I by sin alpha I minus alpha I cos alpha I of KPP. There is no change in this is okay. The error was I missed out this particular bracket when you did the derivation. Okay. I mean, you could have observed it, but however does not matter. So, then subsequently we said the rotation coefficients can be expressed as Ri and Ci. Okay. So, Ri again becomes alpha I times of sin alpha I, okay, minus alpha I cos alpha I divided by twice of 1 minus cos alpha I minus alpha I sin alpha I, and of course, Ci is alpha I sin alpha I divided by sin alpha I minus alpha I cos alpha. On the other hand, friends, look at this equation. This is what we call as Ri and this is what we call as Ci. Okay. That is what we written here, okay, Ri and Ci. And we applied this for 0 axial load as a special case and we derived it, okay, using L'Hospital's rule, and we got for 0 axial load we got Ri at phi I 0, special case is 4, and Ci at phi I 0, special case is 0.5. I think we derived it. Okay. Furthermore, friends, we made a very interesting and comprehensive statement saying that KPP is Ri of Ei by Li, KQP is Ci of KPP, and KRP is KPP plus KQP by Li, which becomes Ri Ei by Li square of 1 plus Ci, and we already know KSP is minus of KRP. This is actually the standard case where this is KPP, this is KQP, this is KRP, and this is KSP. These are the values what we have derived. Similarly, we extended this concept for unit rotation at the kth end. Okay. Then we also obtained the following relationships. We got KPQ as Ci Ri Ei by Li, okay, and KQQ as Ri Ei by Li, and so on, right. So, this is simple. I am giving unit rotation here, okay. This was KQQ, this is KPQ, this is KRQ, and this is KSQ. The second subscript stands for the degree of freedom where we have given unit rotation or displacement. The first subscript stands for the degree of freedom where we are measuring the force. I mean, there is a standard logic we have in the stiffness derivation. We follow the same thing here. There is even not a millimeter change in the whole concept of derivation. Okay, that is the idea why we presented the derivation of the fixed beam first, then we started extending that same algorithm and logic for deriving the stability functions for Euler's load. Okay, that is the idea we have. Okay, having said this, now let us start focusing on deriving rotation functions under axial tensile load. Okay, let us go ahead. Now we are going to do the third part where I am deriving the rotation functions. Okay, they are actually stability functions for axial tensile load, if a beam is subjected to axial tension, then obviously phi I becomes negative, is it not? I have a beam, I am subjecting this to axial tensile load of PA. I am looking for the stability of this. So, if the beam is under axial tension, then we can say my phi I is negative. So, therefore, I now derive or describe a new variable beta I, which is now going to be pi times of root of minus phi I, okay, which I can write as I pi phi I, because you know I square is minus 1. We already know, friends, this pi phi I is alpha, is it not? We already know alpha I is pi square root of phi I. We have used it in the earlier derivation as well. So, can I now say beta I as I alpha I? Okay, let us have this with us. We call equation number 1. We also know that sin beta I, okay, because there is an imaginary function here, right. So, we should say this is equal to E I beta I minus E minus I beta I by 2I, okay, and cos beta I is taken as E I beta I plus E minus I beta I by 2. We call equation number 2a and 2b. Let us substitute this 2a and 2b in this equation 1. Okay. We know that beta I is alpha I. So, let us substituting 1 in equations 2. What do we get? We get the following: sin beta I is E I square alpha I minus E minus I square alpha I by 2I, which makes this as E minus alpha I minus E alpha I by 2I. We call this as equation 3a now. Similarly, cos beta I will be E I square alpha I plus E minus I square alpha I by 2, which now become E minus alpha I plus E alpha I by 2, which is 3b. So, the equations 2a and 2b got refined to 3a and 3b by substituting equation 1 into them. I mean, there is no confusion in this, straight away clear derivation. Okay? I hope you understand and follow the steps clearly. Now, what I do is, we want to give rotation constants at the jth end. Let us work out the rotation constants. We already have them with us. We just now wrote them also, right. So, we have rotation constants. We have rotation constants Ri and Ci. Okay. So, let us copy this. Copy these two equations. Write it here. Okay. We already have. So, we know the rotation constants, which are useful in stability functions. Okay. So, now what I am going to do is, I am going to replace them as beta I. Okay. Instead of alpha, I am going to replace them beta I, right. So, I am going to do that. So, alpha beta I will be I alpha I, you can see that beta I will be I alpha I. So, I am going to just replace all alphas into betas. So, replace all alpha I to beta I, that is what I am trying to do. So, for example, this will become I beta I, I alpha I, okay, and so on, and this will become sin beta I, okay. So, I must get this equation extended there, this equation extended there, and so on, isn't it? So, alpha I to beta I keep on doing this, right. So, let us do that. Please do this, I will do it parallelly here. So, my Ri will now become I alpha I e to the power of minus alpha I minus E alpha I by 2I, okay. This one minus, you can see here is the first term, second term here, minus I alpha I, because I have replaced as beta I here, I alpha I of. So, I should have cos beta I, which is here, okay, this is here. So, let us do that. E to the power of minus alpha I plus e to the power of alpha I by 2, am I right? Let me close this bracket, divided by twice of, divided by twice of this. So, let us do that, twice of 1 minus e to the power of minus alpha I plus e to the power of alpha I by 2 minus, see, this is again beta I, which I say is I alpha I of, then this is sine, I have the value which is e to the power of minus alpha I minus e alpha I by 2I. Similarly, let us write down for Ci also. We have Ci also here. Na? So, again the same story. I alpha I, see here, my alpha I becomes beta I. So, minus sine e to the power of minus alpha I by 2I divided by this one, okay, e to the power of minus alpha I minus e alpha I by 2I minus this value I alpha I of cos. So, e to the power of minus alpha I plus e alpha I by 2. Okay, we call this as equation numbers 4a and 4b, okay, 4a and 4b, which are now the rotation constants for axial tensile load. Okay, 4a and 4b are rotation constants for stability function for axial tensile load. Okay. Now, I can simplify these two equations further. Okay, I can simplify because there are I can just show you a simple manipulation. Let us say if you do this, okay, I will copy this equation to the next sheet, then I will do that. I will copy this equation to the next sheet, then I will do this. Okay. Okay. Let us do this, a simplification. How? Let us say this I and this I gets cancelled, okay, and this I with this becomes minus 1 and that with this becomes plus. So, these are the changes what I am going to expect when I write. So, I am writing this new Ri as alpha I times of E minus alpha I minus E alpha I by 2 plus alpha I times of E minus alpha I plus E alpha I by 2. Am I right? Divided by 2 times of 1 minus E minus alpha I plus E alpha I by 2 minus. This I again goes away. So, I can straight away say alpha I times of, let me write it here, minus alpha I times of E minus alpha I minus alpha I by 2. Am I right? That is my Ri. Let us write down the function for Ci. Okay. So, I can now take a constant and say alpha I plus e to the power of minus alpha I minus alpha I by 2. So, I may change this to plus. Okay. So, what happens is, if you multiply this I with this I get minus here, there is already a minus here, I am putting that minus in the denominator. There is a reason. See, this mathematical simplification is very important, because this is how the standard expression will be reached as you see in the literature. So, let us carefully look at this. So, I am putting the minus here, then I am saying this equation is I think incomplete. It should be, there is a 2i here, there is a 2i here, I think I have not copied that, minus of e to the power of minus alpha I minus alpha I by 2. I am removing this I. When I do that, this becomes minus, I gets cancelled. I am taking I constant out, right, minus alpha I times of E minus alpha plus E alpha by 2. That is my Ci. Call this as equation number phi A and phi B. Okay, friends. Now, I can rewrite this in hyperbolic forms. Now, rewriting phi A and phi B in hyperbolic forms. What is an hyperbolic form? We know that sine hyperbolic alpha I is E alpha I minus alpha I by 2. Cos hyperbolic alpha I is E alpha I plus alpha I by 2. So, I am using this relationship, I am writing Ri and Ci like this. So, Ri now becomes alpha I times of alpha I cos hyperbolic alpha I minus sin hyperbolic alpha I by twice of 1 minus cos hyperbolic alpha I plus alpha I sin hyperbolic alpha. You can look at this simplification, and Ci now becomes alpha I minus sin hyperbolic alpha I by sin hyperbolic alpha I minus alpha I cos hyperbolic alpha. So, we call this equation number 6a and 6b. Okay. These are the expression of the rotation coefficients in terms of hyperbolic functions. Okay. Now, interestingly friends, we can plot this rotation coefficients. We can plot these rotation coefficients under axial tensile and axial compressive loads for a wide range of phi. Phi is a variable, no? Phi is a variable. Okay. These typical tables are available in the literature of stability books. Okay, that is called stability tables. I can say stability constants. They are also called as stability charts. I will show you a typical chart here. So, for different values of phi, R and C are plotted, given in the table for closer intervals. You can also do that. I will also show you a figure, and then I show you a MATLAB program which can plot this. But let us say it is a continuous table which starts from a specific value. So, negative in the table indicates tensile. Positive phi in the table, that is this value. Okay. If it is negative, it is tensile. Positive in the table indicates compressive load. Please understand, both of these loads are axial. Okay. They are axial loads. We are talking about stability functions. Now, where are they used? These charts are useful to estimate the critical buckling load. You may wonder why I am talking about the buckling load estimate. Very interesting question. Buckling load will help you to estimate PA. Now, PA will be compared with buckling load, and if PA exceeds buckling load, then it is a failure, is it not? So, to ascertain whether the structure will have a stability failure under the given load, you must know what is the capacity of the structure to sustain its stability. Okay. So, that is available from PCA. We already discussed that in the stability theory earlier, Euler's criteria. So, now I can estimate this phi, PA, be it tensile or compressive, from this table or charts, compare it with critical load, then I will know. Critical load will help you to estimate from the charts. Axial load is the one which is applied to the system. We can now compare and identify whether the structure will have destabilized mode under this PA. Okay. So, remember, stability charts will not help you to give PA. PA is a known input. Okay. Stability charts will help you to calculate critical buckling load. Okay. So, we have done that. So, now interestingly, we can also plot these charts, but before that let us also do the translation coefficients. Okay, let us also do the translation coefficients. So, let us do the translation coefficients. Let us say under axial compressive load. So, how do you do a translation coefficient or translation function? Initially, I will have a beam, both ends fixed. I will give unit translation to this end. The beam will move here. This will be unit translation. I call this as del R unity. Now, the beam will take this position. So, if this angle is 1 by Li, this is Li, we will agree upon this fact that this angle is also 1 by Li, this angle is also 1 by Li, there is no dispute in this. Okay. Let us now mark the moments and shear causing this. So, this will be KPR, this will be KQR, and this shear will be KRR, and this shear will be KSR, is it not? Now, let us subject this to an axial load compressive P. So, what we have done? We have given unit translation at jth end under axial compressive load. That is what we have done, right? That is the figure. Okay. Now, we will take moments about the kth end. Taking moment about the kth end. Where is the kth end? This is my jth end, this is my kth end of the beam, right? We get, let us see what do we get, PA into 1, that is clockwise, okay, minus KPR anticlockwise, plus KRR into Li clockwise, minus KQR should be 0 sigma m. Okay. So, from this I can write KRR as PA into 1, okay, minus of KPR plus KQR by Li. Okay. What is this actually? Very clear. This is the unbalanced moment in this section, right? Right. So, let us remember this. We call this equation number, I think 5A, 5B, let us call the 6, let us call this 6A and 6B. Now, when I have a member with unit rotation, and this was KPP and this is KQP, this we know, and this was KRP and this was KSP, I think we know this. Okay. We also know that KPP is actually Ri times of Ei by Li and so on. We remember that, isn't it? We wrote it in the beginning itself. See, KPP is RA times of this is CA times of KPP and so on. We already wrote that. Okay, I am going to make use of this relationship now. Now friends, if this rotation is unity, this is KPP. Okay, if this rotation is not unity, if this rotation is 1 by Li, what would be this value? Let us say I know this is going to be KPR and this is going to be KQR. Okay, this is only at the jth end I am talking about. So, can I write KPR as Ri times of Ei by Li of 1 by Li, because this is for unity this value, for 1 by Li this value, is it not? This is only for the jth end. Can I write KQR as Ri Ci Ei by Li times of 1 by Li, because KQR we already have here. KQR or KQP is Ci times of KPP. So, I am using that Ci times of KPP. Okay, I am using that. So, you know KQP is Ci times of KPP. I have just multiplied this with Ci, you can see that here. This is only for the jth end. So, I also have a similar contribution if I give unit rotation at the kth end. And so on. No? So, now I can add that contribution here as this is just swapped RACI EI by Li times of 1 by Li, and this is swapped Ri EI by Li of 1 by Li. We already derived this in the last lecture, you can verify that. Okay. So, what we did is KPR and KQR we obtained, KPR and KQR we obtained. So, we have realized that KPR and KQR are equal. So, we realize that hence KPR is KQR is equal to Ri times of 1 plus Ci times of Ei by Li square. Can I say that? Can I say that? So, we call this as equation, we said 6a and 6b, we call this as 7a, 7b, 7c. Is that okay? Agreed? Okay. Now, it is very simple for me to find KRR. Can I say KRR is sum of this by the span? Can I say that? So, I can say KRR is KPR plus KQR by Li. Can I say that? So, substituting, I will get this as 2 times of Ri of 1 plus Ci of Ei by Li cube. Can I say that? Okay. Now, we should say this is also available to me here. So, comparing these two, can I now say, because 6b should be equal to this, because I am going to equate both of them. So, can I say that K RR is replaced as minus PA by Li? This factor is coming here. Okay, and we also know this will be negative of KR. So, can I say this as minus KSR? Okay. So, friends, for 0 axial load, let me name this equation as 7D. For 0 axial load, KRR is minus KSR is 2R 1 plus CI 2RI, sorry, solve for ith beam, okay, EI by Li cube. Can I say that? Because PA goes away, that is what I will get. Equation number 8. Now, we want to make a general form. Now, to make a general form, both in the presence and absence of axial load, KRR is minus KSR is actually, I am putting a new function Ti of 2Ri 1 plus Ci of Ei by Li cube. I am just introducing a new term. This Ti is called, this equation 9 is called translation function, okay. Translation function. So, now we can say PA is pi square phi I Ei by Li square for n equals 1. Okay. Now, I want to equate the KRR, that is equate 9 equation 9 to or with, compare equation 9 with (7D). We will compare with 7D. Okay. So, I can now say Ti times of 2Ri 1 plus Ci Ei by Li cube is equal to 2Ri 1 plus Ci Ei by Li cube minus Pa by Li. This is what I am writing. Okay. So, this gives me Ti as 1 minus Pa by 2Ri of 1 plus Ci of Li square by Ei, equation number 10. Substituting for PA, we get Ti as 1 minus pi square phi I by 2 Ri 1 plus Ci. B. So, I have now Ri, Ci, Ti equations with me for axial compression, axial tension. Am I right? Is it not? Similarly, I can induce unit translation at kth end and coefficients Kps, Kqs, Krs, Kss can be obtained. What I am trying to do is, I am introducing translation here. Okay, this is 1 by Li, this is del S which is unity. So, this is going to be 1 by Li, 1 by Li, and the moments created are Kqs, Kps, Krs and Kss. Okay, this is what. So, I can compute them. I leave it this a small exercise for you. I am writing the equations for you. So, Kps is given as equal to Krs is minus Ri of 1 plus Ci Ei by Liq, sorry, Li square, Krs, so this is Kps, Kqs, Krs is minus of Kss which is minus 2 Ti Ri 1 plus Ci Ei by Liq. We call this equation number 11a and b, okay, 11a, 11. Friends, please derive this, get it satisfied, okay, before we proceed further. So, friends, I can now write the stiffness matrix by taking Ei constant as this is Ri by Li, this is Ci Ri by Li, this is 1 plus Ci of Ri by Li square, this is minus of. You can easily remember this, friends. If you remember this and this, sum of these two by L will be this and minus of this is this. Is as same as stiffness matrix of the beam member. Okay. Now, to get the second column, swap this. So, this is Ci Ri by Li, this is simply Ri by Li, and this is same as that of the previous one, previous column. Okay. Now, to get this, sum of these two by L, we did the same thing in beams also, isn't it? So, 1 plus Ci into Ri by Li square. Similarly, sum of these two by L, 1 plus Ci into Ri by Li square. To get this, we have to add these two and divide by L. So, there I am going to do the transfer function 2 Ti Ri 1 plus Ci by Li cube. Okay, this Ti is new here. So, this is minus 2 Ti Ri 1 plus Ci by Li cube. Okay, the fourth column is negative of the third column. Okay. So, we have got now the transfer functions which can be quickly plotted using MATLAB program. I will show you the MATLAB program which can be used for this. Okay. I will show you the MATLAB program. So, you can see the MATLAB program on the screen for plotting the stability indices. So, the phi is varied from this range and the degree is converted to radians, and then now R, C, T are computed from the equation, then for 0, for tension and for compression, okay, for compression all the three are computed, okay, then the chart is prepared. This program is available in my reference book. Download the program, run in MATLAB. MATLAB supports you for NPTEL courses through IIT Madras. So, please download MATLAB software, use it for this particular course intensively, okay, this is what it is. So, this is the MATLAB program we have. So, if I do that, my plot for the rotation function R, C and T appears like this. I wish that you should plot this and see yourself how they are appearing, okay, please see that. Okay friends. So, in this lecture we learned the stability functions. We also use the MATLAB program to plot the stability function. We also prepared the chart for stability functions, right. We learnt it for 0 axial load compression, axial load tension. We have developed a generic case, and very interestingly this compares very well with the standard fixed beam derivation without axial load, same algorithm. So, this is also 4 by 4 and the stability function is also 4 by 4, okay. So, there is an absolute similarity between these two in the derivation. So, that is the beauty of the whole exercise. You can easily remember this and try to teach this in the class in the same order. So, the stability derivations becomes very simple, like a stiffness analysis of a fixed beam. Thank you very much friends, have a good day, bye.